All right, so we can go ahead and get started. Hello, everyone. My name is Miss Jessica Finn.
I'm Ms. Kelly Van Horn.
And we would like to thank you so much for coming to our first ever virtual science research symposium. We hope that you and your families are doing well during this very crazy time, and we really do appreciate you taking the time out of your day to come and join us and help us to celebrate our seniors and showcase all of the work that they've done in the science research program. The seniors who are in the program, they've been working really hard on their research for the past 3 years that they've been in the program. And even though we can't come together as one whole group and have our traditional kind of symposium, we are really, really ecstatic that we are able to celebrate them and what they've been able to accomplish in this kind of virtual setting tonight. So again, I thank you so much, and we hope that you enjoy.
So as Ms. Finn said, this is our first ever virtual symposium, and we really do appreciate everyone coming out to see all the work our students have done given the current circumstances. This evening, the juniors in our program will introduce the senior presenters. While the students are presenting, you can type any questions you may have into the Q&A, and the students will answer all questions at the end of their presentations.
Hi everyone, my name is Anna Marie Poposka. I'm a junior in the program and will be introducing our next presenter, Hunter. Hunter is a current senior and will be attending Rutgers, New Brunswick in the fall, and he will be presenting a PowerPoint for us on the production of biodiesel for mechanical application, which is an accumulation of the work that he has done in the program the last 3 years.
All right, thank you for that, Anna Maria. While my presentation loads, my name is Hunter Kolmodin, those of you who don't know me, and I'll be presenting on the production of biodiesel for mechanical application, which is an accumulation of my work. So as an introduction, the exhaustion of fossil fuels is a major issue. Not only do we have a limited supply of fossil fuels, but burning them releases a number of pollutants into the atmosphere. So the production of biodiesel using plants, microalgae, and animal fats have been used as an alternative to this. And a benefit, or the major benefit of this technology is these techniques are carbon neutral, which basically means the same amount of carbon that is released into the atmosphere from burning is carbon that already has been absorbed from the atmosphere. So a brief background for diesel. It's been around since the 1930s. It was first invented by this guy right here, Dr. Rudolf Diesel, who invented the first compression ignition engine. And basically, ever since then, we've seen an increase in diesel and biodiesel. In 1997, there was about 500 million liters of production of biodiesel, and then that eventually moved up to 1.8 billion liters in 2003, which is a big change. So the goal of my research is to generate an electric current powered by a clean biofuel for application. So some of the problems that I ran into with my research, the biggest problems were first, perfecting the process of transesterification. So I'll get into transesterification later more specifically, but basically how it pertains to my research is right here is a triglyceride molecule. It's made up of 3 different fatty acid chains. The first 2 are unsaturated fatty acids, and then the second one is a saturated fatty acid. You could tell by the double bond between the carbon molecules right here. And what transesterification does is it breaks this carbon backbone right here, this blue carbon backbone, in order to get 3 individual fatty acid chains. And these fatty acid chains are hydrocarbons that can be burned just like any other fuel or diesel. And another thing was extracting the long fatty acid chains. So there's short chains and there's long chains. The short chains aren't really as beneficial in biofuels, so that's why it was important to use a source that would have long fatty acid chains. And then the third, and probably the biggest, was eliminating a glycerol byproduct. So when I ran my experiment multiple times, I often got this solid glycerol byproduct, which is unuseful because for gasoline, you don't want to be putting a solid in your tank. So basically, eliminating that was the priority. So one article that really helped me in my research, right here, it basically explained the process of transesterification and how it needs to be done specifically for vegetable oil and biofuels. So it basically stated that in a transesterification reaction of vegetable oil, you need 3 moles of methanol, which is used as an organic solvent, are required to react stoichiometrically for every mole of triglyceride molecule. And then the second article was more focused on using algae in order to extract lipids, and it tested different strains of lipid content and extraction methods. This helped me really understand the different ways to lyse a cell and isolate fatty acid chains. It determined that the most effective way to lyse was using microwaves, and the most effective algae strain was Botricoccus b. So my first goal was to derive 100% biodiesel from vegetable oil. So this was done using these materials. I used 1.75 grams of potassium hydroxide. This was the catalyst in the reaction. 250 milliliters of used vegetable oil, which is just vegetable oil that's already been cooked with, and 100 milliliters of methanol. So those were the 3 main chemicals in the reaction. And then I also used a mason jar and a heat source to heat up the vegetable oil. So the first thing that needed to be done was the methanol need to be titrated with the potassium hydroxide. The potassium hydroxide is the catalyst in the reaction, and methanol is too volatile just to use by itself, so that's why they needed to be reacted with each other. This exothermic reaction of potassium hydroxide with methanol leads to an equilibrium reaction to potassium methoxide and water, which avoids the formation of a highly inflammable gas, which was important when I was running this experiment. So transesterification. So transesterification is basically when you have 1 alcohol and 1 ester, and then by switching the R groups, you can see in the reaction down here, it creates a different alcohol and a different ester. So once methanol is titrated, it can be used as an organic solvent to break down the triglyceride backbone, as I said before, into singular long fatty acid chains, as long as we get these R groups to swap right here, which would break down the carbon backbone. Basically, we need to use the alcohol to detach the carbon backbone, and then the ester attaches to the fatty acid chains individually. So the used vegetable oil, I heated it to about 65 degrees Celsius using a hot plate and thermometer. And then I used the potassium methoxide mixture and added that to the vegetable oil, which was in the mason jar. And then I shook that vigorously for 5 minutes to make sure everything was reacted, and then I let that sit for 2 days. So this was a result I got. It was just about 94.3% clean biofuel, which was actually a better result than I thought. I thought there would be more glycerin and a soap product, but it turned out there was only 5.7% glycerin. So the glycerin basically was on rise to the top of this mixture right here, and then I was able to take it out using a pipette. So the second part, or the second stage of my research, involves a 5-volt motor, which is powered by a Stirling engine. So a background on Stirling engines. They're a relatively simple design of a heat engine that's operated by a cyclic compression and expansion of air. They were used in the 1800s to power submarines and generate forms of electricity, but were eventually replaced by steam engines that were replaced by diesel engines later. So you can see in this diagram right here, a Stirling engine works through the compression of air. So as air heats up, it expands, forcing this piston to move out. And on the other side, as heat cools, it compresses in, forcing the other piston to move in, and then it's just a constant cycle turning in axis. So the assembly of my Stirling engine, I was able to find the parts of the Stirling engine on Amazon, and then I could assemble it together. There's a picture of it on the right. You can see that there's an upper and lower plate, and also you can't see, but inside there's an upper and lower chamber where the heat is applied through the bottom directly. So the bottom has a chamber, and then that's where it expands. So it works out pretty convenient since the heat could just rise to the bottom. It also operates in a closed cycle, which is important because if it wasn't closed, the pressure and volume would just be released. And the way I burned my biofuel was on a wick. As you can see, or you can kind of see, I'll show you a better picture later, but there's biofuel in this bottom cup, and then we just used the wick, tied it up, and then lit at the top, and it burned pretty effectively. So what powers the engine is the temperature difference between the two air groups. Right here, this is Charles' law that states that volume of one group over the temperature of one group equals volume of second group over the temperature of second group. So basically what you can derive from this equation is if there's a bigger difference between these two groups, the faster the engine wants to move because it wants to constantly be in an equilibrium state. The Stirling engine is held up on a stand that I made where the reaction of biodiesel can take place below it, so the heat rises to the bottom plate. The chain that is linked between the axle and on the engine on the small motor is a rubber band that actually works pretty effectively if there's a decent, or not a lot, but some tension between the motor and the Stirling engine. And the motor is connected to, I used a 25-watt halogen bulb to show it working effectively. So here are my results. These are going to play. All right, the first video on the left, this when I did it in class, it wasn't actually connected to a motor, but you can see it, the Stirling engine turning from the flame on the bottom. The only problem is overheating. So basically, the bottom plate, when it starts to heat the whole thing, it starts to slow down. It starts to slow down. So that's why you have to do it in cycles. The second video, you the chain and motor, and then the third video, I get the best view of the halogen bulb lighting up as the Stirling engine was turning, the 25-watt halogen bulb. Okay, so as a discussion, the burning rates of biodiesel is about 38 megajoules per kilogram, depending on the type, and petrodiesel, or just regular gasoline, is 43 megajoules per kilogram. Therefore, you need about 1.13 times as much biodiesel to get the same amount of energy, and will therefore produce around 2.8 kilograms of carbon dioxide, which every kilogram of fuel burned. So basically how the biofuel burns, it's very similar to a candle where there's a wick, and the wick is able to keep burning as long as there's a constant source of biofuel. The biofuel isn't that reactive, but if it's heated up enough, it'll be flammable on touch if it's hit with a flame, but it doesn't ignite. So as a conclusion, there's many factors that affect the quality of biodiesel. This can be the type of source oil, the way the cell or the fatty acid is derived from. The catalyst also plays an important role. I used potassium hydroxide, which through all my research said that that was the best catalyst to use. The temperature of reaction makes a difference. You don't want it to be too hot or too cold. It'll slow it down. So basically, this picture on the right here is from Utah Biodiesel Supply. It shows the difference between used and new biodiesel. On the right is what it means is new biodiesel, as in vegetable oil, is clean. So from the new, you can see that there's just a biodiesel layer and a glycerin layer, just two. And then for used biodiesel, you get different shades of color, number one. But another thing to point out is there's a soap layer. The soap layer just comes from all the debris that's in the used vegetable oil. And a bottom glycerin layer that's a little better, that's a little bigger. But basically the biodiesel layer that stays on the top is what you want to extract it from. So mixing biodiesel with diesel has been effective. B20 is actually a popular blend. It's 20% biodiesel, 80% petroleum diesel, which some cars operate on. Low-level biodiesel blends such as B2 and B5 are actually very good fuels in the trucking industry because biofuels have very good lubricating properties. And yeah, so basically petroleum will continue to be a main source of diesel until it is more cost effective to switch to organic sources. So through my research, I was able to derive biodiesel from vegetable oil, but at the end of the day, it's still cheaper just to fill up with your gas can at the Exxon, which gas prices are pretty low right now. But yeah, hopefully we can get to that point one day. Yeah, so if anyone has any questions, you can ask them now. I'd like to, before I end, I'd like to thank Ms. Finn and Ms. Van Horn for helping me in my research a lot, really. And I'd also like to thank Dr. Brinkman, who helped me my first couple of years in starting my research. And I'd like to thank my parents for supporting me too. So, good. Okay, so all right, Ganesh asked, does the Stirling engine in efficiency over time? As in, won't the chambers lose their temperature difference over time? Yes, so where eventually the Stirling engine starts to heat up. So you want one chamber to be hot, but you really want the temperature difference to be there. So actually, when we ran the experiment over time, yeah, the engine started to slow down. So that's why it's important to keep it on different cycles of cooling. Okay, so also another question, Ms. Slazak. Earlier in your presentation, you mentioned investigating the lipid contents and how those affected biofuel production. Would plant-based oils with lower lipid contents produce less of the solid byproduct? Yeah, so when I first was running my experiments, I was using like a rice type oil, and then we actually used corn oil, which I'm pretty sure they had a different lipid content. So the plant-based oils with lower lipid content, with the plant-based oils with lower lipid content produce less of the solid byproduct. Yeah, so that wasn't something that I was actually able to determine, but I assume that was one of the factors in the glycerin byproduct. All right, and what was the cost it took you to derive biodiesel compared to petroleum or other commercial diesel? I did not actually calculate the cost, but basically the most costly product would probably have to be the catalyst, even though you only use a small amount of it, but also the vegetable oil itself is pretty costly, but definitely more expensive. The biodiesel is definitely more expensive to make than the petroleum or other commercial biodiesels. All right. So if there's no more questions.
Montville Township Public Schools. Educate, inspire, empower.